Welcome to OpenFace, an adversarial attack on facial recognition. There's a growing body of work contributing to thwarting facial recognition systems. The state of the art is to use a physical object worn directly on the face. On the left, we see a mask, which, when worn, warps the face to the point where facial recognition has trouble even knowing that a face is there. On the right, we see a type of glasses which, when worn, causes a facial classifier to misclassify the person as somebody else. Our project provides a novel approach to this body of research by projecting directly onto the face. To do this, we develop a high-quality facial classification system on a set of 8 people and use machine learning and other techniques to then figure out what we can project onto the face to lower the accuracy of our facial recognition system. Our setup is very simple, using only a camera mounted on a projector stationed 1.4 meters away from the user. These are connected to just a personal laptop. We use 2 main tools to help create a facial classification system. The first is a Python library called dlib, used for facial recognition. This allows us to create a bounding box around a face in an image and crop and warp it so that the eyes and nose are in the same place every time, and the image is 96 by 96 pixels. This pre-processed image is then fed to an open-source facial classification tool called OpenFace. OpenFace takes this image and spits out a 128-dimensional embedding. The main property of this embedding is that 2 images of the same person will be clustered together in embedded space, meaning small Euclidean distance. In this picture, we have a 3-dimensional example of how different faces will be mapped close to different clusters of points. Each color represents pictures of one person that are embedded by OpenFace. To be able to classify a specific set of 8 people, we have to train a small neural network using the output of OpenFace. OpenFace does all the work of recognizing important features of an image and embedding it in the small space of 128 dimensions. A simple neural network is then able to classify specific people from your training set. To figure out what to project onto an image, we first started with digital modifications. There are 2 main types of digital modifications we use. The first uses dlib to find the locations of important features on a face, such as the nose or mouth, and then add extra color. The second approach is to use an adversarial neural network to learn to minimally modify an image such that the classifier will still incorrectly classify. Our system requires a 90% facial classification accuracy to show that our techniques work on even a high-quality classifier. Our main objective is misclassification, which is to cause the classifier to output any wrong answer. This corresponds to a drop in classification accuracy. We aim for at least 50% drop in accuracy. Our secondary, more difficult goal is targeted misclassification, where we choose a single person and hope to get the classifier to always output that person as the answer. We require a projector accuracy of within 1 centimeter, which is the distance between where we think the projector should project on the face and where it actually projected on the face. We aim for the frame rate of our system to be at least 10 frames per second, which is to say that we take an image of a person and project the intended change within 1/10 of a second. We tried 2 different neural network architectures to produce our projection. The first is a convolutional network. The second is a densely connected ReLU network. To calculate loss, we run the output of our adversarial network through OpenFace and the classifier. We have 2 different loss functions that we used. We have a loss function for misclassification, where the network is penalized if the classifier is able to classify correctly. For targeted misclassification, the network is penalized if the classifier gives any answer besides the target person. Here are examples of digital modifications made by our networks. The convolutional network tends to apply a sort of colored filter to an image. The dense network tends to cover the image in colored dots. The convolutional network was able to achieve an 88% drop in classifier accuracy, which far exceeded our goal. However, it failed to achieve targeted misclassification at all. Our dense network was able to achieve a 95% drop in classifier accuracy and a targeted misclassification rate of 97%. This was an unexpected and happy success.
We came up with a second modification method, which uses dlib and is more of a human-based approach as opposed to a neural network. Firstly, it takes in an image, then uses dlib to extract the facial landmarks, and then obtains the convex hull, which is simply the shape contained within the set of landmark points. This modification will then be overlaid on the original image. This is an example of what a modification of the mouth would look like. Next, we have an example of a nose modification on Claudia, and the result of this is that the classifier misclassifies her as Eugene.
This is our projection setup. So we have the projector right here, we have a camera, and they are coaxial with each other, and the projection is projecting essentially the points that would have gone on my face. So right now what I'm doing is DLib gives us various points on the face. So it gives points on my mouth, points on my jaw, points on my eyes, and points on my eyebrow. And I'm taking those points that our camera detects and I'm projecting onto the various points of my face. So right now it's frozen. So I'm going to move it one frame. What's going to do? It's going to capture a picture of my face, find the points on that face, and then we're going to use the projection method that we created to project those points onto my face. So this is it projecting onto my face. One thing to note is first that it's not extremely clear when it's projecting onto my face versus when it's projecting onto the wall. You can even see the pixels. Another thing to note is that our process takes about 1 second versus the 1/10 of a second that we originally planned to use. How we project is we start off with the checkerboard pattern on the left, and then the camera will be able to see that, and it will be able to create a correlation between the points at the corners. Then when we see something on the camera, then what we can do is we can use those correlations to map a point to the other point. This is how we figured out how close our projection was off of the original. So here we just have an image that's being projected of me, and we projected that image with the DLib points in red squares. You can kind of see a little bit red, and then we overlaid based off of how we calculated where the projection points should go onto these points. So if you compare the distance between the blue and the red points, then you should know how off the projection is. Here we have two examples of me being classified successfully. Both of them I am being projection on, but with nothing in particular, just a black screen. So here is an example of the DLib modification projecting something onto my nose. In this first image, I'm successfully classified, and in the second image, I'm misclassified despite the modification. This is an example of the DLib modification to my lips. In this first image, with the modification, I'm successfully classified, and in the second image, with the modification, I am not. So here is an example of the architecture 2 projecting various points onto my face to attempt to misclassify. With the projection, I'm misclassified in this image, and I'm also misclassified in this image, but I am successfully classified in this image despite the modification. So this is architecture 1 projecting essentially kind of like my face, but more green. You can see it right. I was successfully classified in this image, and I was misclassified in this image due to the modification.
Our results show that almost all our metric goals could be achieved digitally, but things were not as successful when done in real time with the projector. It is difficult to ensure accurate projection every time, since the individual is probably not completely stationary, and this is something that we could improve on given more time. Our usage of the two different modification methods also shows the advantages of using a neural network as opposed to just making manual changes. While it is possible for human-made modifications to thwart a facial recognition system, an adversarial network performs so much better at achieving targeted misclassification. Overall, our project demonstrated that good facial classifiers can still be vulnerable to attacks, and given that facial recognition technology is getting increasingly popular nowadays, this is something that should be considered. So this is Snowface, our project. Thank you.